Hey everyone, welcome. Today we are unpacking the absolute ultimate tool for hardware verification, UVM Sequences. Whether you're a novice trying to wrap your head around the fundamentals, or you're an experienced engineer looking to really refine your verification skills, this explainer is designed to give you a deep, highly practical mastery of how sequences actually drive testing. I mean, UVM has become the undisputed industry standard for a reason, right? It brings real software engineering rigor directly into hardware verification. And mastering sequences, well, that's literally the key to unlocking all of that power. So let's dive straight into the million-dollar question that every single hardware verification engineer faces when building complex test benches. You might have a massively complex system on chip designed, but how do you actually mimic the chaotic real-world traffic it's going to experience once it's manufactured? We're talking about totally unpredictable user inputs, intersecting data packets, sudden hardware interrupts, and just messy bus contentions. Hard coding all of that? Yeah, that's practically impossible. And that brings us right to our core definition. Think of your test bench as a stage setup, with instruments. The driver, the monitor, the sequencer, they're all just sitting there waiting. But the sequence, that is the actual sheet music. It's an object that encapsulates user-defined procedures to generate a continuous stream of transactions. It's basically the brain that tells the test bench exactly what to play to create realistic stimulus for your DUT, or design under test. By encapsulating these procedures, we keep our test logic entirely decoupled from the physical connections. It's a real game changer. Here is our roadmap for today. We'll be covering 1. Demystifying UVM sequences. 2. The sequence engine methods. 3. Understanding the execution flow. 4. Read, write, and random. And 5. Real-world sequence usage. Let's get right into it. Section 1. Demystifying UVM sequences. Let's start by separating the stimulus generation from the static test bench hierarchy to unlock maximum reusability. Now, this quote from the UVM manual really refocuses our attention on the ultimate goal here, realistic dynamic testing. By keeping the sequences, which are the actual behavioral tests, completely separate from the physical test bench hierarchy, you guarantee that your stimulus can be reused. Think about it. You could take a memory test written for a single block and seamlessly reuse that exact same test at the top-level system, or honestly, even on an entirely different project, without having to rebuild the environment from scratch. When we think about the UVM object hierarchy, the sequence classes extend straight out of the transaction base class. Because UVM is built so heavily on object-oriented programming, our sequence items inherit a really rich set of features. Extending from UVM object is incredibly powerful because it gives your transactions built-in methods for copying, comparing, and printing data right out of the box. So the UVM_sequence_item is your base for a single transaction, while the UVM sequence extends that even further to generate entire streams of those items. Section 2, the sequence engine methods. Let's step into the engine room and see how this builds into actionable execution using the core API methods. We've got 3 core methods that form the mechanical heart of literally every sequence you'll ever write: body, start.item, and finish.item. If you master how these 3 work together, you understand exactly how UVM drives hardware stimulus. This is the essential machinery, the gears turning under the hood, that bridges the gap between your abstract test ideas and the actual pin wiggles on your hardware. Okay, so let's break down the first piece. Your main sequence logic lives right inside the body task, and this is automatically executed via the start method. This is your user-defined sandbox. But, and this is a huge but, why should you never call this method directly? Well, it's because the UVM phasing mechanism and the start method handle all the necessary pre- and post-execution callbacks entirely automatically. If you call body manually, you're bypassing critical framework steps, which leads to nasty sequencer deadlocks and just bizarre simulation errors. So definitely don't do that. Now, to actually launch an item down to the driver, you've got to strictly follow a chronological order. First, you create the sequence item. Second, you call start_item. Third, you randomize the item's variables. And fourth, you call finish_item. This highly specific order allows for what we call late randomization. By randomizing after start_item, you guarantee the transaction is generated using the absolute latest state of the simulation right before it goes to the driver. When you're actually coding this execution flow, you've got some options. You can write out the 4 manual steps we just talked about, or you can leverage macros like UVM_do_with_prior. These macros are great. They elegantly condense the creation, starting, randomization, and finishing into a single, clean line of code. But a quick word of warning, while macros save a ton of time and visual space, understanding the underlying manual steps is absolutely crucial. When you inevitably find yourself deep in a debugging session trying to figure out why an item didn't generate correctly, knowing those 4 steps is what will save you. Section 3, Understanding the Execution Flow. Let's unpack the intricate dialogue that happens between the sequence, the sequencer, and the driver during execution. This maps out the transaction-level modeling, or TLM, communication dialogue over simulation delta cycles. It shows exactly how a sequencer requests permission before sending any data. At t+0, it issues a request and waits for a grant. Then at t+1, once granted, it sends the request, and finally, it waits for the item to be physically driven. The sequencer is basically acting as an arbitrator here, making sure that if multiple sequences are running simultaneously, traffic is handled fairly without chaotic collisions. It's honestly a perfectly choreographed cooperative dance. This sequence provides the data, waiting for the arbiter's grants, and the driver actually wiggles the hardware pins. Crucially, the driver must explicitly signal completion using item_done to keep the flow moving. If your driver executes a transaction but forgets to call item_done, well, your sequence remains blocked forever, and your simulation will completely hang. That right there is a mistake that costs engineers hours of debugging time, for sure. Section 4, Read, Write, and Random. Time to translate all this theory into the bread and butter of your daily tasks with some applied practice. Think about the pure symmetry of the UVM Register Sequence API. When you're writing sequences for hardware registers to poke and peek at your design, you really don't want to get bogged down in routing logic. A write sequence naturally uses write_reg, and a read sequence uses read_reg. Using these dedicated, symmetrical methods keeps your stimulus incredibly clean, super readable, and focused purely on the data being moved across the bus. What's really cool is how the Convenience API completely abstracts away the need to manually pass the parent sequence argument. Methods like write_reg automatically inject .parent_this under the hood. It might seem like a minor detail in the grand scheme of things, but it's a brilliant design choice. It saves engineers thousands of keystrokes over a project lifecycle and drastically reduces visual clutter in those massive test benches. But beyond direct reads and writes, we rely heavily on random sequences. Constrained random generation is practically a superpower of SystemVerilog and UVM, especially compared to the directed testing we used to do in older languages. By leveraging this right in the middle of our start and finish calls, we dynamically generate legal, robust stimulus on the fly. You just define the rules of what's allowed, and the solver automatically blasts your design with thousands of varied scenarios you might never have even thought to hardcode. It's brilliant. And that brings us to Section 5, Real-World Sequence Usage. How do we actually take these building blocks to the system level? Out in the wild, verification engineers use these exact mechanics to wrap up insanely complex operations, like entire network protocol stacks, into single reusable objects. Imagine bringing up a complex SoC. You might have several sequences running totally independently, all managed by a master virtual sequence. A virtual sequence is incredibly powerful because it controls multiple other sequencers without being tied to a specific hardware interface itself. It acts as the ultimate system-level orchestrator. So the ultimate goal here is that by combining these modular sequences, you can aggressively hunt down obscure corner cases without rewriting your core test bench. Because sequences are simply class objects, they can instantiate and execute other sequences. You build up a library of small, highly focused unit tests, and then you compose them hierarchically to create massive, intricate test scenarios that just push your design to its absolute breaking point. So as you architect your next verification environment, really ask yourself, how can you leverage this sequence engine to build smarter, more reusable tests? By mastering the body task, the execution handshake, and reusable virtual sequences, you are essentially building a bulletproof verification environment. The beauty of UVM is that once you've mastered this flow, there is virtually no limit to the complexity of the stimulus you can design. Thanks so much for joining me on this explainer. Keep optimizing.